this cutoff frequency, we will see the role of the attenuation in the input signal when it will pass through this amplifier. So if let's say we are having a frequency very low, so let's say this frequency is low, 0 divided by fc, so AF divided by under root 1 will be the answer. So voltage gain will be AF, only AF. If this frequency is high, if F is high, then the equation will become, this thing will become greater. So F is very greater than FC and 1, and we will have under root F square. So now high frequency is in denominator, so the gain will be AF divided by F. So gain is reduced if frequency is increased. If frequency is infinity, gain is 0. So there is an inverse relation between gain and frequency. This product is known as gain bandwidth product. Gain bandwidth product, and it is always relatable. So this equation suggests that this equation suggests that the gain will always decrease if we increase the frequency. So this is the summary of this slide, that we want our gain to be high, so we keep this frequency low, so gain will be high. Okay, the voltage gain at various frequencies is given in this slide. So we are using the same equation as did in previous, and we are saying that F is less than FC. Remember that in the previous slides we were discussing the bandwidth of the amplifier, not the FC. So bandwidth of amplifier is determined by the physical structure of an op-amp, but FC is determined by the combination of R and C. At very low frequency, where F is less than FC, the output by input, the gain will be equal to AF, because we proved that this thing will leads to a 0, and this AF by 1 will be our voltage gain, AV. Okay. At frequencies that are equal to FC, we will be having a 0.707 roll off, and 0.07 is minus 3 dB. So when FC is equal to our frequency, the cutoff frequency, the gain will be minus 3 dB. And this can be calculated from this, that when F is equal to FC, this will be, let's say, x by x, and x by x is 1, and A divided by 1 plus 1, which is A divided by under root 2. And if we take log of this under root 2, so this is 0.707A, and take log of this, we get minus 3 dB. So that's why we say that minus 3 dB is also known as half power bandwidth, because at this particular frequency the power becomes half. Okay, at very high frequency, the V out by Vn is less than AF, because the denominator is big. So AF divided by big is smaller gain, so the gain will be lesser than the DC gain of the amplifier. So this is pretty much it about the voltage gain at various frequency for a low pass active filter with amplifications. Okay, now coming to the high pass filter. High pass filter is just same as the low pass filter, but here the things get interesting, because we are having a limited bandwidth amplifier and a high pass filter. So this high pass filter also uses RC circuit, and this RC circuit is drawn in here, and its FC is 1/2 pi RC as that of in the passive circuits, passive filters. After that we are using this non-inverting amplifier. So non-inverting amplifier is again having a full feedback of the signal, so that turns out that its AV would be equal to 1 again. So we will see a role of with an amplification of 1 for the whole circuit. Okay, so this design is pretty much same as that of the high pass filter with passive circuit elements. So we will skip this whole circuit and we'll go to the next slide, in which we are having the divider circuit. So here we are having the same gains, and its voltage gain circuit is almost same as the previous one, except that we are having an extra F by Fc in the numerator. So here F is 1 R1 R2 plus R1. F is the frequency which is being analyzed, the signal frequency or the frequency that is given on this port, and Fc is the calculated frequency for these two components. So Fc would be equal to 1 over 2 pi C1 R3. Okay, just like the low pass filter, the operation of high pass filter can be verified from these equations. So at low frequency we will have V out by Vn lesser than AF. So now it will be for low frequency. For high frequency it will be almost equal to AF, and for intermediate frequency, which is Fc, it will be minus 3 dB. So now the things are reversed due to this factor in this amplification. The introduction of this component in here is due to this capacitor. So if we remove this capacitor from here, we will not see any F by Fc in here, as we can see in this circuit that here is no part in here. Okay, so this is due to this series capacitance to the circuit. Okay, so this is pretty much it for the high pass filter with amplification, and this is the voltage gain equation for this. But we can never get a perfect high pass filter on active devices. That problem was discussed in previous section, but here is the graphical representation of that. Due to the fact that the denominator is having F by Fc, so high frequency will make the denominator high. So if this denominator is very high, this circuit will become, let's say, 0. So 0 multiplied by F by Fc will gives us 0. Mathematically this equation is correct, but physically these are two separate equations. The first equation is, let's say, this one, and the second equation is, let's say, this one. So two separate equations. If this first equation gives us a 0, the second equation, even if it is in millions, it will not amplify this voltage. So the graph for the first part is this one. It is having an Ft, the total terminating frequency, and after this this graph will touch the 0 axis, the 0 dB axis. So if we have such amplifier and we pass a high pass signal, we pass a high frequency signal to it, the upper band would be deleted from it, and we will only have such a response. So this is why we can never get a perfect high pass filter on the active circuits. So this is a flaw which makes this thing only usable for low frequency usage, but low frequency usage is still very much effective for such amplifiers. We can never say that these amplifiers are useless, because till these ranges, till let's say 100k frequency range, we still have much more uses of these amplifiers. Okay, now the active band pass filter. Active band pass filter is a bit different from that filter that we studied so far. In previous filters, we introduced the amplifier at the output. So we had a circuit, we had a circuit, and then we had an amplifier on the output of it. But in bandpass filter, what we do is that what we designed for the bandpass filter in previous passive filters, we use the same circuit but introduce an amplifier in the middle of that circuit. So this is our that amplifier. We have introduced it after passing through the signal through the high pass filter. So this is our high pass filter, and it is having an amplifier with a gain of 1 over R4 by R3, which is the DC gain, and after that this DC gain is ADC divided by 1 plus F by FC whole square under the root, which is the AC gain, AAC. So this circuit is introduced in the middle. So after having a high pass filter, we pass it through this amplifier to make this thing steeper, to make this thing like go like this, and after that we pass it through a low pass filter. So low pass filter will cut some of range from it, so it will make things like this. So this is our high pass filter, this is our low pass filter, and this is our filter out signal. The high pass signal is high, the low pass signal is already amplified, so this is high. So we make this thing go up, and this is already up, and only we need amplifier. So after the second stage, we do not need any amplifier in here. Why we do not need? Because it is already amplified. So one way of making this simple active circuit is by basic passive high and passive low pass filter and the use of operational amplifier as given. Okay, so this the previous one was the non-inverting style of amplifiers. Now we are discussing an inverting amplifier. Inverting amplifier has again equation a bit different than a non-inverting. In this again is non-1 plus R2 plus R1 plus R2 by R1. It is not like that ADC, but it is minus R2 by R1 because the feedback is on the inverting end. Okay, so this is the only difference in it. The rest, the structure, etc., are all same, and the formulas are discussed in the previous slides. Holds for this as well. You can check this thing on the link that I have provided as well. Okay, so now talking about the resonance frequency point and the Q factor. So resonance frequency point is almost the geometric mean of FL and FH. So if this is our whole frequency band, this is our FL, this is our FH. So F low, F high, this is from 1 over R2 C2 2 pi, and this is from 1 over 2 pi R1 C1. So these are two frequencies. If we find the geometric mean of this frequency, it would be like this. So this is FL into FH. So this is FR under the root जो हम करते हैं तो FR बन जाता है. The maximum gain of this amplifier is calculated for R2 divided by 2 R1 as in here. The Q factor, the quality factor, is determined by calculating the ratio of FR with the 3 dB bandwidth. So 3 dB bandwidth is actually our bandwidth between FC1 minus FC2, let's say. So this is our bandwidth of 3 dB, half power or 3 dB bandwidth. So this gives us this frequency. If this thing is low, if the center frequency is low and the bandwidth is high, so we are having a low quality factor. If this thing is high and this bandwidth is low, So we are having something like this. So it is a notching effect, and it is of high quality factor. So high quality factor means that we will have a very sharp cut or sharp rise in the frequencies. Now, discussing these cuts and rises, we use the mathematical format known as the Butterworth filter. An ideal electrical filter should not only completely reject unwanted signal but also have uniform sensitivity for unwanted signal. So it should follow some rules, and these rules are written in this equation. In this equation, that the filter must have a transfer function like such. This n represents the number of active components that we are using. So normally this is the order. So active components direct proportional to the order. So more active components, more high order filter. So more components, more no active component, the inductor or the capacitive components. So more stages in the amplifier means more high roll-off. So Butterworth filter is a type of signal processing filter which is designed for frequency response, and flat response can be obtained in the band pass filter by increasing the this value of n in it. The Butterworth filter roll off more slowly around the cutoff frequency than Chebyshev and elliptical filter, but without ripples. So Butterworth filter is something like this. If we use some other type of filter for high roll off, what we will do is that if we cut this thing like this, it will make this signal to vibrate something like this. So Butterworth is the most smooth filters of all. We can check the higher order filters in these graphs that Butterworth is the more smoother filter, but its response is slow. Its response is slow. This response is high, this is again high, this is very high. So the most higher response is of elliptical filter, but again it is introducing a very high ripples in it. So sharp cut means that we will have something like this, and low cut means that we will not have some ripple. So this is about the higher order filters. If you want to learn more about these things, you can go through these useful links and let me know if you have any questions in it. We will also perform these filtering techniques in labs, so you will know more about it. These divider circuits are not in our course. We will just study the unity feedback systems, unity gain system. So for that we do not need to indulge in these equations. So I guess that is it for our today's lecture. Thanks for listening to this lecture on the active filters. Thank you.